Hello, welcome to another module of this course, Microwave Integrated Circuits. In the previous modules, for the past few weeks, we had covered the topic of stability. And as I had said, stability is a very important aspect of amplifier design. And in this module, we'll be covering about amplifier gain, how to design an amplifier with a given gain. So already we have discussed about the various types of gain that we talk about. Among them, the transducer gain is the most effective. It is the most practical definition of gain. But then the problem with transducer gain is that we cannot design gamma S and gamma L independently. Hence, to get rid of that problem, we had some other definitions of gain like operating power gain and available power gain. And then I had also mentioned that for the unilateral case, that is when S12 is equal to 0, the definition of the transducer gain can be somewhat simplified. So let us start the discussion today on how to design for the unilateral case where we have S12 is equal to 0. Now this GS or GL I can write by the general term like this. Now for an unconditionally stable case, we have seen that SII modulus should be lesser than 1. This is of course considering that this case where the stability circle is encompassing the center of the Smith chart. Now for this case, we have SII lesser than 0. And our GI is between 0 and some value GI max. Now if we define a term small gi, which is defined as follows. Say capital GI is the gain that you want to achieve and GI max is the value of the maximum gain, maximum value of GI, where GI is either GL or GS. Then we know that GI max is given by this equation, and GI will verify this equation. This in turn verifies that GI, small gi, is between 0 and 1. Now the locus of those values of gamma I which give a constant GI, and that is a circle, and the equation for that locus is given by this, where Ci Ri is given like this. Now, the center of all the circles for the various values of Gi are located between 0 and Sii star. So, if we draw a line between Sii conjugate and the center, then all the centers will be lying on that line. The other observation we see is that Gi is equal to 1 for gamma I equal to 0. So, in other words, Gi is equal to 0 dB, that is, there is no gain for gamma I equal to 0. So, if we now go to the slides on the monitor, we see that if we draw these circles, then it will the circles will look something like this actually. Now, what is these red circles are these gain circles or the locus of the gamma I for a particular value of capital Gi, and this blue circle is the Smith chart. The other thing to note, as I had said, is that the line joining the origin of the Smith chart to this Sii conjugate, the center of all these red circles will lie along this line. Now, what we had so far discussed is for the unconditionally stable case. Now, what happens when we have a potentially unstable case? In this case, the GTU will continue to be written by this formula. And this can go all the way till infinity. That is the difference between a potentially unstable and an unconditionally stable, is that there is nothing called a Gi max actually. For the unconditionally stable case, we have a certain concept of Gi max. For that we don't have. Now, we don't have such a thing for the potentially unstable case. Now, this happens when 1 minus say Sii gamma I, this becomes equal to 0, then Gi will tend to infinity. The other thing about stability is that it requires, if say again, if we draw our basic 2-port diagram, now for stability, as we have already seen, this is the condition, and if we write it in a different way, then this thing can be written as now. The question is that if you see that, since writing this in this way, now ZS or ZL both will have positive real parts. So, we can say that real of Zi will always be positive, and not only positive, but greater than the negative of the negative real part of Z11 or Z22. So, since the negative of the negative real part will be positive, that is why we can write this equation like this. So, then what is that, writing it in a different way will also, we can say that the real part, since the real part of Zs or Zl should be greater than the modulus of Z11 or Z22, the locus of gamma s and gamma L can be expressed in this form. If we go back to the slides on the monitor, you see the requirement for stability is that the real part of Zi should be greater than the modulus of real part of Zi. This in turn translates into this circle. So, this is our stability circle for Zi. Now, you might ask here that how is this stability circle different from the stability circles we have already covered so far. The difference is, for those stability circles, say you are considering Z11, then the locus will be for ZL, whereas in this case the locus is for Zs. That is why it's not, we cannot apply the same theory that we discussed for the previous case. What about the gain circles? That was about the stability circles. But what about the gain circles? So, for the gain circles, our definition of small gi remains the same, which is small gi is equal to so the definition remains the same. However, note that we do not have any concept of GI max here. There is no concept of GI max. However, the definition remains the same, and the definition of the Ci and Ri also remain the same. That is, Ci is equal to Gi times Sii conjugate upon 1 minus Sii square and Ri is equal to that is these definitions remain the same. And based on this, if we again go back to the diagram on the slide, the gain circles that we have drawn are like this. Now, if I just compare with the previous one, we see that the Sii, the center, or we had obtained a Gi max for gamma is equal to Sii star. The question here is, what is this Sii star for this potentially unstable case? Now, we note one thing, like in that Sii star, since there is, see, first of all, there is no concept of Gi max, okay. So, there will not be a point for which the radius is 0, that will not happen. However, if we have to locate the line along which all the circles will have their centers, then we can, instead of plotting S11 conjugate, we simply plot 1 upon S11 because 1 upon S11 has the same phasor as S11 conjugate. That was about the gain circles, but about the impedance matching. Suppose this dotted line, the small circle that we see, is the gain circle for some value of capital GI, and if we go from, and if we have to provide a matching network. So, first of all, note that this is the value of gamma s that we have to achieve, and for matching we need we need this gamma s to be matched to our characteristic impedance, which say for our case is 50 ohms. So, as we know, for matching what we do, we find the path from the center to that particular point. And why take this particular point, by the way? We could have taken any of the points along this dotted circle, and all the points of this dotted circle which lie in this white region will be stable. Why do we choose this point? We choose this point because this is the most stable point. This has the maximum, this creates the most, I can say the most or the highest, or gives the highest value of the real part of Zs plus Z11. That is why we choose this point. Alternatively, we could have chosen this path as well, from the center to this point gamma s, which is the most stable point. Now, in this case, going along a constant resistance circle upwards means inductive in series, and then going upwards again along a constant conductance circle also means an inductance, but in shunt. So, in this case, our matching network for the previous case, where first we went down and went up. So, going down along a constant conductance circle means a capacitor in shunt, and going up along a constant resistance circle means an inductor in series. So, that is what we have here. We started from 50 ohms. First we have a capacitor in shunt and then an inductor in series. In this case also, first we will have a inductor in series and then an inductor in shunt. Alternatively, if we go along this path, where first we go down along a constant resistance circle and then go up along a constant conductance circle, here also we will first have a resistance and a capacitor in series, followed by an inductor in shunt. There is a certain term called unilateral figure of merit, or unilateral approximation figure of merit. Now, we know that GT, the real value, without any unilateral approximation, is given by this equation. Now, GT upon GTU will be given like this. And then on further simplification, this comes out to be like this. And suppose I denote this quantity by the term x, then this whole thing comes down to now, depending on what the value of x is, whether it is positive or negative, we can say that this gt upon gu, this equation, you can work it out, you can see that it is true, you can verify that this is true. The maximum value of this gt and gtu will be when this is equal to 1 minus modulus of x square, and the minimum value of gt upon gtu will happen when this value becomes equal to 1 plus modulus of x square. Now, GTU max, as we know, is obtained for gamma s equal to S11 conjugate and gamma L equal to S22 conjugate. Now, for that particular case, if this is the value of gamma s and gamma L we take, then this GT upon GTU max will be given by so this will be the range of GT upon GTU max if this is the condition, that is the maximum gain case if we take. Now, here this ux is given by, let me use a different piece of paper. This is the value of ux. So, if our this GT upon GTU max should be between this range, okay, and whether or not for a particular GT, whether we can make this approximation of naught depends on this value of ux. If our GT that we obtain does not lie within this range, then we can say, or this ratio, if this GT upon GTUX, anytime this ratio is not within this given range, then we cannot do this unilateral approximation. So, usually the value of u, say a usual value of, or a particular value of u, if it is 0.03, then GT upon GT max will be so this GT upon GTU max, if it is not within this range, then we have a problem. We cannot do that unilateral approximation that we have been doing. So, in summary, in this lecture we covered the case when we have the unilateral approximation valid, and we saw what happens to the gain circles or what are those gain circles for both the unconditionally stable case and the potentially unstable case. In the next module, we shall be covering the case when we don't have this unilateral figure of merit, and then we shall see that our choices are somewhat limited. We cannot design it. We cannot do as much flexible design as we have been doing so far, that is choosing any particular gain. And also how to design using the operating power circles, power gain circles, and the available power gain circles. Thank you.